But at some point you would suddenly, and the autonomous system will give the success control back to the driver. At that time, what's the level of trust that the driver needs to have that he's taking back the control? What's the situation? What's the level of information that you need to be presenting to the driver who was previously not involved with the driving, but now it's suddenly getting involved? What's the reaction time? So that's where you have to take into consideration the human factors, how human things react. You have got to build that into the intelligence system. That's where the research that we were discussing before is neuromorphic, human intelligence and machine intelligence coming together. How this things become important. The fourth priority was census requirement and optimization. We had the luxury of over instrumenting our light water reactors these days, but going back to advanced reactors and microreactors, the size are shrinking. We don't have that luxury anymore. Or we have to think about multimodal sensors. We have to think about virtual sensors, how optimally to place them. And because real estate is a luxury right now. So we have to think indifferently. A multimodal was not a part of our existing fleet, but it's going to be part of the future fleet. And what sensors can also sense external disturbances and how they can feed into it, so that. The fifth area was probabilistic risk assessment, very specific to siting and transportation, because we didn't have the risk. We don't have the tools to do PRA for multimodal transportation needs. We have it for spent fuel. We can consider spent fuel as a part of a reactor, but still with the reactor transportation and microreactor on the trailer, microreactor on an airplane, microreactor on a shipyard, it's different analysis, different risks scenarios, different hazard that you need to take into consideration. So scenarios and the consequence is different. And so you got to build tools around that. We can build on the existing tools, but we need to understand the base events that would impact those existing tools. The third is the decay heat removal challenge to ensure safe and reliable operation, because one vision with the fission battery is should be mobile. Going from manufacturing site to site A for operation, and then once the purpose at site A is moved, either you can go back to the manufacturing place or you can move to a new location of site B. And during that time, this reactor has been activated, right? And if you have to move it in a short notice, how would you take care of the decay heat process? How would you protect it from the shielding thing? One option is put it on the ground vault approach. But again, then you have this transportation issue. You need to open the vault, take it out and move it. But also, then you have to build a decay heat system under the ground that takes the heat distribution away. And the sabotager can take advantage of that and choke the heat distribution system, and that will destroy the reactor. So we have to think in how the heat removal system and shielding would work. So that's where we have. So as we mentioned, the visibility of fission battery, we had NRC coming out and looking at this symposium very closely and the initiative. And what we consider as a good progress is they are drafting the microreactor licensing strategy right now. And they have acknowledged some of the work and the vision that we have in the fission battery initiative, and as I've included in the draft version of the white paper, as they strategize the licensing of the microreactor, which is a big thing because microreactor is at a different level of autonomy. And we talk about a much higher level of autonomy. So they want to understand how the economic technology would transition from the current state to the levels of autonomy to achieve either remote operation or completely unattended operation. So that is a huge thing that we think as this initiative we have achieved, is creating a vision, visibility, and a thinking process within the NRC that this can be done. And we also have a Rev 0 of the R&D plan of the fission battery. I'll be more than happy to share that with this group, or with the IDO group. It's open, it's available for external release. We are working on the second version of this, which will have more advanced discussion on some of the technologies, and I'll also highlight some of the ongoing projects in this area. So that's the visibility. Hey, and then we also have an open special issue on addressing the innovation challenges of technical issues with fission battery in the Progress of Energy, Nuclear Energy Journal. So I think so that the initiative that at Purdue who aligns with some of the innovation challenges, or would address some of the innovation challenges that we are seeing in the fission battery initiative. So and the focus of this year is to work on the lightweight materials. What are the challenges? Whether it's a qualification challenge, whether it's licensing challenge. So what are the challenges, and what are the research gaps? How we can address those gaps and do R&D. So that's what the focus is. We are planning the workshop. We want to have it in person, so we'll see. So probably later in the spring or summer semester, we'll have this extensive 1 or 2 days workshop on lightweight materials. So we will extend the invitation to everyone, and so we want the best in the materials research world to come and share their thoughts on what are the challenges with developing lightweight materials for nuclear application, especially with the extreme conditions in mind. And we also have an ongoing project with NA21 on understanding what are the cyber vulnerabilities and safeguard vulnerabilities to achieve autonomous operation, because autonomous operation requires integration of hardware, software, and communication. So there are multiple vulnerable points or threat vectors that can go wrong. So that's where we are working on cyber digital twin approach. Why digital twin? Because there is no physical model or operating experience with any of the advanced reactors. So we have to rely on digital twins. And we are going to leverage some of the ongoing work at Idaho National Laboratory on a heat pipe microreactor, where we have the digital twin of a heat pipe microreactor. We're going to transform that to become a cyber digital twin of a heat pipe microreactor and do some vulnerability assessment. So that's probably my last slide, and I would like to acknowledge it's a team effort. I'm just leading it, but it's a huge team effort from the National University Consortium, INL team, and other administrative staff. So that's the vision on the fission battery. I would be more than happy to address any questions.
I have a question.
Yes.
That's a very stimulating discussion, let me say. I'd like to extend it into the development of distributed energy resources, because a battery is nothing more than an energy storage device on demand. And you listed 5 attributes, but by the time you take in distributed energy resources that are both AC and DC distributions, as well as renewable and non-renewable resources, you can add other attributes like it has to be responsive within microseconds, distributed, redundant, available and accessible, secure and safe, convertible, movable, and licensable. Now, you mentioned some of these in your presentation, but there are many others, I think, that have to be added.
So some of them that you mentioned are embedded in some of the thinking, like unattended attribute would be addressing the response time. Then standardization wouldn't address the other needs. And so I think so. You're right. There are a few more we can include, but I think so. As we go forward, everything will get embedded into this 5 accordingly, which serve as a best house for that.
Yeah. No, I agree entirely with you. This is just a starting list that needs to be integrated and rationalized. But I think you have to start with a longer list to begin with, just to be sure you didn't leave anything out.
Okay. Yeah, that as we get more feedback, we just either say it's part of the existing list, or we just brainstorm more and include one additional attribute. Yes.
All right. Well, thank you, Professor Biman. Thank you, Vivek, Dr. Agarwal. I know you have a hard deadline in just about 1 minute or so. And this is just an appetizer. You got us excited, and we're hungry for more. So I'm just going to ask you right now to commit yourself to a keynote speech on the subject, a keynote lecture on the first CiENS Intelligent Energy System Symposium later this semester. It will be in the 26th, I believe, of April. I will send out invitations. Hopefully the pandemic will be over. Hopefully we can have you here and we can have these exciting discussions, because this is the future. It's a paradigm shift. And I think there's a lot we're going to have to, produced in the innovation space. And here is the place, one of the places to do it. Thank you so much, Vivek. We don't want to keep you from your next commitment. Have a wonderful day. And again, we appreciate what you laid out for us, but we take it as an appetizer. We want the main course later on.
Okay.
Thank you.
You for the invitation again, and we'll be more than happy to entertain any more questions and discussion on this topic.
Thank you, and we'll give you a strong round of cyber applause. And
Thank
have
you.
a wonderful day. Thank you, Vivek.
Thank you.
Thanks. Okay, so we're going to move on to the next presentation, which in fact, it will be my presentation. We did this in order to, we put Vivek first because he has this commitment. Sort of my presentation is really the way, sorry, if I find it here. Okay, folks. Asvini, can you help me with putting this on, or do I?
Yeah, sure, I can do that.
Thank you. Oh, I have it here, but somehow it didn't show. Okay, so thank you, Asvini. So this is now the raison d'etre for the center is really, do I have control? Do I move it this next slide, or you can, Asvini, would you help me?
Yeah, I can move it for you.
Yes, this is, so it's me, it's Lefteris Tsoukalos, and I'm going to give you a little bit of background why we came up with this and how with the center, and what sort of direction we're heading into. Next slide, please. So I will present the CiENS community locally, mostly locally, the people who have been involved in setting this up. A couple of words about the green transition, or the net zero by 2050 for others. The connection between energy and AI, machine learning, the various scales, and some of the unique digital facilities we do that can enable the development of these ideas. Next slide, please. So the list is long, and I won't be able to refer to everybody by name, but definitely Dean Chiang deserves our gratitude, our great gratitude. He moved this initiative forward. Dean Chen also, and Professor Kim, Sung-Tai Kim from chemical engineering, the head of chemical engineering, has been involved with a lot of the discussions and really has inspired and guided us on how to proceed. I'd like to thank Professor Peroulis, the head of electrical engineering. I'd like to thank Professor Karava, who is an expert in buildings, smart buildings, and her discussions and presentations have helped us, has inspired us. And Dongyan Shu, the director of CiENS, who is helpful in providing not only a working example of a successful center, but also a lot of the ideas about digitization and AI and so forth. Dongyan is a professor of computer science. Nathan Sudheis and Andrew Liu and Joe Rasmus also were involved in the early stages of this. There's a huge intellectual debt to Arden Biment, because about 20 years or so, he started an initiative called CIMEG, this Consortium for the Intelligent Management of Electric Power Grid. And this was an EPRI-funded and DoD initiative that very early on looked at the connection between energy, electrical energy, and the internet, and means of responding to the demand autonomously, locally, with signals such as prices. So it was really pioneering. That's where it all started. I think we all learned a lot about the connection between the power system and the internet, thanks to the spearheading efforts of Professor Biment. Also that to Eugene Spafford, who set up probably the most successful center in the history of Purdue, the CiENS effort. Unfortunately, Spaff, wasn't not be able to be with us. This is a morning full of commitments, and we didn't get everything in time for these things. So our apologies to Eugene Spafford. Dr. Darema has been an inspiration for us throughout the years. He retired in NSF and then later in the Air Force Office of Scientific Research. We'll hear from Professor Ali Brandis, who is our power professor. George Gross from Illinois has been a supporter and a friend and a good friend with a lot of insights into where the power system would go. Many thanks to Professor Kais, the eminent professor of chemistry, the materials. I'll talk a little bit about the scales later. And Professor Goodhart, our good friend and scholar from the liberal arts side of Purdue, John Sutherland from Tripoli, and a lot of the connections with the climate and the ecology, emergencies we're facing. That to Professor Tsouffanidis, who is, I hope, with us, and he's always been the sort of the guy that taught us that information and radiation are connected, or that radiation is a form of information. We'll hear from Professor Murtaguno from Georgia Tech, and the many people like Vivek in the national labs. I haven't listed them all here, but definitely Alex Heifetz has been an inspiration, and so is Ken Patel. Dr. Padazopoulos, one of our great alums now in London. I hope he can hear us. He's provided a lot of the ideas for cyber security before these ideas, before the 2000 scare, the bug for the Millennium Bug. There was a group of people here, including Gene Spafford and Elias Hustis and Kostas Padazopoulos, who did pioneering work on cybersecurity. So the community is extensive, is diverse, is multidisciplinary, is environmental, and is also a reflection of the energy community around the world. Next slide, please. So why the CiENS, why the Purdue Center for Intelligent Energy Systems? It is to bring this diverse community and to host research and educational opportunities and facilities and programs, put a grand roof under all of this, particularly because energy gets digitized and gets digitized at different scales, and that has its own implications and research and innovation challenges. So we want to bring this community of researchers and academics together, put our heads to solve some of these great problems, but also to be able to imagine and work on future directions, strategies. So what energy digitization and digitalization, as some call it, will bring in the future and where we should be heading there. But all of this is under really the grand challenge of a green transition. It's making electricity production free of carbon emissions, and that's much bigger challenge than anybody can imagine or easily say. To make this while the grid is still standing, the power grid, it's safe, it's efficient, resilient, and hopefully even cheaper. But this is really truly a grand challenge. It's a big challenge, and we need new talent, new ideas, and new efforts to address it. Next slide, please. So we see now energy for many people, especially electric power energy, which is the sort of highest form, is not the biggest part, by the way, of total energy, as we will see in a moment. It gets digitalized, it gets really innervated by the internet. Historically, it has been seen as a legacy area, an infrastructure that works. It has evolved over more than 100 years. And a lot of the engineering has been on the supply side and building generators and wires and power stations and substations and so forth, and sensors and SCADAs. But with the innovation from information and internet communication systems, there is a shift of focus on the demand side, and we see now real-time price-directed demand being a possibility, not just for large factories, large consumers of electricity or malls, but also for anything that plugs in the wall. For residential, all devices can have microprocessors, and they are on the internet, and the process of managing the power consumption can be seen as a proxy. Can be no different than managing a bank account, and that can have important implications for saving energy. Some of the electrical energy we generate goes wasted because we have to be ready to get, it's a peak demand constrained system. On the other hand, the network, the information network, it's a bandwidth constrained system. So bringing this together, it's not as easy or transparent or as resilient as it seems at first sight. So intelligent energy, it's a way to fill these gaps and to make progress. And there is research and policy, as we saw already, the hint that fission batteries will require NRC changes, maybe not even, will not just be power, national or regional or local power utilities, but international companies that will manage these batteries. So we have new issues. They tie very strongly with the geopolitical, with the ethics of using AI and having some autonomy, in these machines, or possibly even engaging in, through blockchain, in tokens that can be of energy, that can be exchanged, much like the cryptocurrencies. We're talking about the international security and the geoeconomics and the ever-changing phases of globalization. In education, we need new content in our curricula, new online programs, and possibly badges and certificates that people who have mechanical or electrical engineering orientations can get credentials in economics and informatics and at all different levels. We're going to need new skills, new sets of skills to design the scientific engineering design and operate and decommission these new infrastructures. Next slide, please. So if we look at the world energy picture, this is the ground picture of all, 265 billion barrels of oil equivalent per day we need. This is the total energy, of which the actual world, the oil demand is about 100 million, and the supply is about 100 million barrels per day. Really, and I think the supply is about to take over, even though we're still not completely out of the pandemic. The pandemic created some savings because of the severe recession it caused in 2020. But we have problems, the supply side and the demand side. The demand is very young because it's fueled by the populous regions of the world, Southeast Asia, India, China, of course, but the supply is old, aging, and is really struggling to keep up with the demand. And it's about, it's at a point where we see a lot of critical instabilities, because unless you have supply which exceeds by 5-6% or more, the capacity to supply has to be greater than the demand. In the 1970s, when we had major oil crisis, the excess capacity that we call excess capacity was about 50%, and now it's practically zero. So we're going to have a tight situation, the supply-demand balance in hydrocarbons. And some people say it's better to try to reduce our consumption. We leave oil and gas before they leave us, and they're about to leave us. But when we look at the big picture, we see that 80% of the total energy the world is using is still fossil fuels, mostly oil, but coal and gas increasingly so. And only about less than 20% comes from nuclear, hydro, and renewables. And as you know, as we speak, there's a huge energy crisis in Europe. Prices have skyrocketed. There's a infrastructure, a global infrastructure of markets and systems to address these problems. If it was 60 years ago, we would be talking about the Berlin airlift, but we had something as great and important as the Berlin airlift of 1962, but it's done silently, it's done through the markets. In the last month or so, like 8 weeks or so, about 40 LNG tankers that were heading from the North American, origins, the Gulf of Mexico, they were heading for the Asian markets. They were redirected through pricing signals from the international markets, the spot markets of gas. They were redirected to Europe, and they provided about a month's worth of gas, 10% of the annual EU demand. And so the result of that is that, there will be margins to not have catastrophic blackouts because of the situation of last summer, and because of some policy, maybe optimisms, if not mistakes. The EU, as you know, the EU has many EU states have banned, fracking. They don't want shale gas. They don't want nuclear. They want electricity, but that electricity has to be produced somehow. So we have, there was the risk of a lot of people suffering or hurting, or even worse than that, dying in Europe from cold in the dark because of the lack of gas, but that has been ameliorated. And it's an example of how signals can be helpful in directing resources and allocating resources in these international markets, which are structures of rule-based, information systems. So next slide, please. But hydrocarbons are extremely important, not just for energy generation. They're the basic feedstock we have for fertilizers, for materials. And so the fact that the supply and demand is very tight and the demand exceeds supply, basically, it's something that should worry all of us, because it's not just keeping the lights on and keeping warm. It's also bringing food on the table, medicines, the whole workings of the global economy and the local economies are based, and the balanced economic ideas that Dean Chiang mentioned earlier at the boundary of these infrastructures. They will be without hydrocarbons, to fuel our factories, not just for energy, but feedstock, right, for materials. We would be having big problems in the workings of the world. Next slide. And you can see this as the way that is projected on the CO2 emissions. If you look at this graph, is CO2 emissions, they went from less than 5 billion tons per year up until the 1950s. And then from the 1950s, they take on and they go to 35, close to 40 billion tons of CO2 per year. This period from 1950 to today is what historians of the future will call the oil age, the petroleum age, because after World War II, petroleum takes off, and really, it's the way we built the roads and the schools and the hospitals and fuel the factories and all the agricultural revolutions, the green revolution that is capable now of sustaining more or less the largest, a third of all humanity that ever lived, about close to 8 billion people. But this is problematic. I need not tell you that we are in a climate emergency. Whether it's real or not, it doesn't matter. And maybe climate changes have happened and will be happening all the time. But we have to be cautious, and the world is deciding to bring that 40 billion tons of CO2 emissions per year down to the level of about less than 5, so practically 0. And that's the energy transition. Let's go to the next slide. The International Energy Agency, the branch of the OECD in Paris, have created a roadmap for this transition, and says that about 70% of all consuming nations and all consumption in the world has agreed or is agreeing in some form to this map. So India will have net zero by 2050. We'll actually have it by 2070. China by 2060. but the advanced sort of economies of Western Europe and Japan and the United States are agreeing as 2050 the deadline for transforming the energy production, the electricity production, transportation, which is a big part. It's bigger than electricity, big contributor of emissions. The biggest probably is transportation, and also industry, cement, fertilizers. So this grand challenge, getting to below 5, getting to before 1950s in terms of emissions, this grand challenge, meaning it has huge implications. It will call for an innovation revolution. $117 trillion investments by 2050 is akin to what happens after wars. So we see we will have a lot of capital destruction and a restart. So a lot of capital would be needed. Low interest rates, this whole thing is not going to be easy. It's really visionary. There will be risks. There are risks. The IEA may be a little bit optimistic, but the gist of all this is you can't do this without innovation. Innovation is the way to proceed with hope, not with denial or blissful ignorance. And innovation starts at in many ways at universities. It doesn't stop here, but one of the crucial things in the long chain of and the long road of innovation is to prepare scientific and engineering talent, and that's what we want to do. If you look at the roadmap of IEA, of the International Energy Agency, there's some tough things. There will be no sales of internal combustion engines after 2035. After 2030, there will be no sales of trucks except those who are using electric batteries. And this is hard to imagine, because I think last year, 2021, there were licenses in Europe for maybe 40,000 trucks, internal combustion engine trucks, and only six of those are electric electric battery trucks. So how we will get there is easy to see in the roadmap, but it will be very difficult in reality. And the sort of the exegesis for having even the daring courage to imagine this is really innovation. Innovation is the answer, and we're going to have to work very hard, especially at the university levels, and that's part of the agenda that CiENS wants to claim, to play a leading role in the US, in the world, in abetting this road to a net zero by 2050. Next slide, please. So the different scales of this, I call it nanowatts and terawatts, although we're talking about energy, I choose, power quantities. And nanowatts is, of course, the materials level, it's the semiconductors, it's the imaging, it's the research, the energy quantities of the research, the start of innovation, including the quantum computing, including the cool things that we will need to do for getting over Moore's law. Terawatts is, of course, the policy and the planning is where a lot of, 1,000, power plants, would be 100 power plants, will be producing. So the key here is to view scheduling, and this is an idea that came out of Arden's pioneering effort. Scheduling, if we are scheduled, we are able to exploit complementarities, asynchronisms. We're able to use scheduling as a form of energy storage, or because a battery can be also the amount of energy that you're not using and somebody else will use it. So this scheduling is a problem we solve through intelligent tools, computationally, through AI. The system is too big to really, we can schedule in our own homes, we can schedule what, if we know that the power of electricity will be a lot cheaper at night, we can charge our batteries for the car, or, do our laundry, and, maybe some of the other energy intensive things at times that the prices will be favorable. So scheduling can be, it's a computational task. We use the internet to do it. And we can't do it really without AI and ML. It's too complicated, to do it at a system level. So the smart grids, this is what came out of the CiENS effort and demand response. The demand, that is everything that hooks to the power system, can be regulating its own behavior through pricing signals. So then we talk about smart cities, we talk about energy and non-fungible tokens, like these cryptocurrencies. We're going to have a new and fresh view on the ethics of these systems because of the considerable amounts of autonomy. But autonomy doesn't mean we dump the human out, and how this relation between human and the machine takes place is really something that we have to go back to the basics and look at the ethics, not just as morality, but also as know-how. We need new storage, even though storage can also be the scheduling problem to offset, the unwanted use of our energy. Hydrogen, both in the sense of carrier, we all know hydrogen is very problematic, but we can have hydrogen enriched fuels. We can have hydrogen, for fuel cells in this integrated system. The power plants can augment their production at peak times through hydrogen-driven fuel cells. And of course, energy reliability now is the big question when we connect things to the internet, and the big issue of small modular reactors, including these battery-like reactors like the NMR. The NMR, the Novel Modular Reactor, is a 50 megawatt reactor. It's designed here at Purdue. Next slide, please. So to do all this, we need test beds, and Purdue has two unique test beds. It has the Purdue Reactor University Reactor 1, which is the first and only digital reactor as far as instrumentation controls goes in the US, and it has PUMA, the scaled version of a full, advanced design of a nuclear reactor. So these digital facilities, we need test beds. Nobody will license an energy system, whether it's a network of nuclear batteries or chemical factories working on schedule that is affected by prices, or refineries, or nobody will do this without verified and validated approaches. And for that, we need test beds. And Purdue is a great university. It's one of these great universities that don't throw things away, doesn't throw things away when they're done, when their funding cycle ends. And we're lucky in that respect because we have, these are the only two that we know from the School of Nuclear Engineering, but there are others in the university. And the center, CiENS, aspires to make this available, to organize a structure, an architecture, bringing this community together. And as we said, as you systems people know, structure implies function, and the function here will be to make these facilities available to researchers outside, within Purdue and outside Purdue, for testing, validating, and developing and licensing ultimately these new approaches. So next slide, please. Well, you see a glorious picture of our Purdue University Reactor 1, digitalized and upgraded with new control rooms and so forth. Next slide. And here is PUMA, 500 instruments, digital instruments. It's a full power plant, including all systems for protection and control. And it serves as an engineering design and a manufacturing prototype for Purdue's novel modular reactor. Professor Isi and Professor Sunjun Kim, Professor Evanker, Professor Bertudano know about how to build this. We have built it here. We know how long it would take. It can serve as an exemplar for manufacturing small modular reactors like the NMR. Next slide, please. So here we are. CiENS is about to start. We have this opportunity to have facilities that we can open to the community, the broader community. We would like to host an intelligent energy symposium here at the end of the semester to build an industrial visitors program, and by industrial visitors, we mean also people from the national labs, from government. I was delighted to see that in Vivek's seminar, a symposium, a third was government, a third was university, and a third of the participants were from the national labs. So I will stop at this point. Thank you very much for your attention. Next slide. Maybe we have time for a couple of questions. If not, we can proceed and have some questions at the end of our meeting. Any questions? If there are no pressing questions, we'll leave them for the after the talk of Dr. Darema. And at this point, maybe 2 minutes ahead of time, I'm surprised nobody has a question, but I'm not so surprised. It's not actually everybody wants to respect. Questions from Professor E? No? Are you muted? Okay, so we then we move to our next topic, and I'd like to invite Professor Mertoguno from Georgia Tech. The Achilles heel of this digitization of energy is really cybersecurity, because yes, you can have batteries, you know, and like the Tesla cars, you cannot, you know, lift the hood to see what's happening in case there is a problem. But the company knows because everything is monitored, you know, through, you know, these monitoring centers. So there will be no control rooms. There will be, you know, long fuel cycles, maybe 10-year refueling or just replacing of these batteries. But all of this depends on the ability to protect these devices and new digitized energy systems from cyber attacks, from, you know, fake operators, from, you know, malicious, you know, problems that emerge out of competition or terrorism or all kinds of things. And, you know, energy is probably one of the, besides defense, is probably one of the most critical infrastructures for national security and global security. So Sukarno Mertoguno is, Karno, are you there?
Yep.
Okay, is one of the world's expert, great expert, and it's a great, you know, policy person. He was at the Office of Naval Research for many years before joining Georgia Tech. At Georgia Tech, she's the Chief Innovation Officer of for the Information and Cyber Sciences Directorate of the Georgia Tech Research Institute, which is the research arm of the university, the institutional arm of the university. Sukarno's expertise in developing innovative cybersecurity solutions. He managed basic and applied scientific research in cybersecurity before joining Georgia Tech. In accomplished software for the Office of Naval Research. He was a system and chip architect for you know, Silicon Valley, San Francisco area companies. He has a PhD from SUNY Binghamton with focus on system architecture design, and he has a degree in theoretical physics from the University of Indonesia. So Karno, as we call him, our dear friend and great colleague, the floor is yours.
All right, let me try to share the screen. Oh, no. Can you see my screen? Let's see here.
Not yet, Karno.
Hold on. I don't know.
You want Ashwini to?
Yeah, I have my slide, I think. On can you just?
Yeah, I'm happy to share those.
Okay, thank you, Ashwini. What would we do without you? We wouldn't have a meeting. Thank you. And thank you, Carnal,
All right.
for joining this morning. It's a great privilege to have you. Thank you.
Thank you. Yeah, what I'm going to talk right now is about the basically mechanism kind of approach to cybersecurity. Mechanism means that it does not require any knowledge. This is the dumb one, but this can function as the last line of defense against cyber attack and any cyber disruption. As you know, I mean, if we use a lot of machine learning, you need to have something else to back it up if something goes wrong, right? Because with machine learning, it is a statistical method. As such, the only guarantee you have is guarantee to make a mistake, and you need to have something else just in case the mistake happened, right? So that's the way we look at it. And this was invented when I was at the Office of Naval Research, by myself and also with the help of many universities. So what we are going to talk here is this is about the controller, right? What is cyber-physical system? The cyber-physical system is a cyber system that interact with the physical system, right? Next slide. So if you look at it, cyber-physical system contain two subsystems, the physical subsystem and the cyber system. The physical subsystem is governed by physics, and the cyber system through actuator try to control the behavior of the physical system. And this coupling is somewhat loose because one side, the physical system, is actually on continuous domain. The cyber system work in this discrete domain, and there is a looser connection here. So if we look at the IT system itself, the IT system, the cyber system, the cyber system has two kind of different systems. One is the IT-like system, which more complex and has a lot of communication. And then the other one is the controller system. Each of the controllers deals with the one or a set of actuators that control the physical system, right? I mean, normally, in this IT space security on the IT side, normally for security, you do monitoring, intrusion detection, etc. This is where knowledge is required, and in the cyber physical system, it's rather easier compared to the normal general purpose computing, because there is a process model, there is an expectation. You can create a digital twin here, so it's a little easier and a little stronger than than security that is applied to the general computing system. Beyond that, then there is the communication. So what you do is encryption and authentication. The same thing on the controller space. You have a way to actually model the system. So there is a digital twin kind of monitoring and detection that you can do. You can also have encryption and authentication. One thing here is normally the processing capability at the edge, at the controller, is limited. So you really don't want to do anything really heavy. And the other one is that mechanism. This is knowledge independent. This is what we try to do here, basically to complement the rest of it, right? So next slide. So in cyber physical system, the cyber is actually a play a supporting role. It's a means to an end. The most important thing here is the primary concern is the stability of the physical system. So the goal here is how do we guarantee that the physical subsystem is stable and behaving as expected and not necessarily to make the cyber subsystem stable. Next. So in here, there are two important properties of the cyber physical system that we can use to help us achieve this goal. One of it is the periodicity, right? The controller has a scan cycle, and this is generally from 1 Hertz to 300 Hertz for a small drone, right? When I surveyed the Navy, when I was trying to do this, the sweet spot, most of them fall between 3 to 12 Hertz, right? That is the scan cycle. Because of scan cycle, because of the periodicity of a cyber physical system, we actually can tolerate some loss of input. We can lose event and the physical system, and later on we can rescan it, and we somehow can recover that. Not completely, but that's signal that is lost, but what is important is the later signal anyway. So periodicity allow us to tolerate loss of input. And then there is an inertia, which is basically the behavior of the physical system. The nice thing about the inertia is actually it allows us to lose some output. So we can mess up some output control as long as it is not too long, it's not too much and too long, the system will still be stable because the physics doesn't even know that, right? So inertia provides some natural tolerance, even if it is limited. Next slide. So normally in the critical cyber physical system, we have, such as reactor, we have redundancy often. Right. I mean, I know for sure that the control on the aircraft use QRC, which is quad redundant control. And there is also Byzantine fault tolerance. So there are fault tolerant systems that have been built and proven effective for physical and random failure for ages, right? We know that. The problem is cyber attack make all of the controller, the redundant controller, goes into a common mode failure. So fault tolerant cannot defend against cyber attack. So now what we need to do is having all of this knowledge to build a fault tolerant system. How can we turn it into a cyber attack tolerance, right? So next slide. So before we go there, the first thing that I'd like to say here is that there is an invariant in cyber attack. So cyber attack can virtually thought as having two phases. The first phase is to attack the system to derail the original system program, right? And then the second one is to gain control. We thought both of these attacker is not successful. So if you look at, an analogy to this is a football. Right. So in order for an attacker to get the ball, he has to tackle the guy who has the ball, right? The defender who has the ball and the ball fumble, and he has to pick up the ball. Otherwise, the ball will just fly and roll across the field, and basically the attack fail. When the attack fail, the attack fail basically it can be translated that the system crashed. When the system crashed and restarted, basically the defender get the control again, not the attacker. So for the attacker to gain control, it has to be successful in both steps, right? Derailing the target program and capturing the control, right? So if we want to address, so because it has two phases, if we want to address the security from the first phase, which is better, right? If you can avoid getting tackled at all, that's great. But in cyber, it means that your software, your system cannot have any bug and flaw whatsoever, which is very difficult, right? One way to do it is probably with formal method, or you put a lot of protection in the in your software implementation, but that's not even guarantee 100%, right? Even for a method cannot guarantee 100%. So that's difficult. Making the second, dealing with the second one is easier and cheaper. This is basically you have to put randomness in your system so that it's not predictable. So you know this can prevent the attacker from gaining control. So one way to do this is to increase, to introduce artificial diversity. Next slide. So if you look at it, our design essentially is based on the Byzantine fault tolerance, and what we do is that let's say the C0 is the original program. What we need to do is we need to diversify C0 and create a version C1 that is a diversified version of the C0. And then we also want to engineer C1 so that when it crashes quickly. We want to crash quickly, right? I mean, we'll talk about it later. And there are tools to do this. These are the things that has been built at ONR and also at DARPA that can do it at the source level or binary level, right? So that's tools that we can use, and then if we want to have a stateful recovery or warm backup, then we introduce a delay FIFO here, delay input sharing, to help us with that. So if you look at it, right, so C0 and C1 is, the input is sent in parallel to both C0 and C1. And this is essentially or analogous to having two locks and given one key. So for an attacker to attack it, it needs to use that key to unlock C0 and C1. Obviously, he cannot, right? So that's the guarantee here. Next slide. So let's try to see how it works, right? So if you have a normal Byzantine fault tolerance system, if there is a cyber attack, so cyber attack is divided into two stages, right? So the top one is the diverting is actually the first phase, and own is the second phase. So if there is a vulnerability, then divert always happen, and if the attackers know where to jump or to gain control, then it can own the system. So if there is an attack, a system like this will be owned. It does not crash, but it's now under control of the adversary. Next slide. So now if you diversify it, right, you have C0, C1, and C3, all has vulnerability because we don't even know where the vulnerability comes from. But the process to gain control are different, right? So next slide. So if there is an attack, and what happened is the first C0 is owned because the attacker know how to attack that, but the C1 and C2 both crashes, right? So yes, but this is not, it's not any good, right? Because you have one output that is not crashing, it's actually corrupted or owned by the system, and the other crash, it cannot give you any output, but this can be detected. Next slide. So if all you want, if you can deal with the, if your system is not stateful, then you can just restore it from the backup and it's good. But if you need to have a warm backup or maintain a known good state, one way what you can do is you can do checkpointing. But on legacy system that we dealt with at the time at the Navy, that's kind of expensive and kind of too disruptive. So we do another way. Next slide. So we introduced this delay FIFO, basically, right? So the hope here is that when there is an attack, we can guarantee that the C2 here, the backup, is not corrupted. Next slide. So here, if there is the attack comes in, C0 is on, C1 crash, but this is an indicator that, the crash is actually an indicator that the system is under attack. But because the attack input is still in the FIFO queue, C2 are clean. So we can use the state of C2 to basically, control for a time being, and also use the state of the C2 to restart C1 and C0, so that it does not have to start from initial state, right? And the requirement here is that the delay queue is long enough so that the crash happen before C2 get corrupted. So next slide. So that create the equation here, basically the requirement of BFT++, a system that are within this requirement or satisfy this equation, we can apply BFT++. This is basically saying that there is a delay queue of so many slots, and the crash the time to crash should be smaller than the delay queue. And then the delay queue itself, or the time is smaller than the tolerance that inertia gives you, Dd, minus the time for recovery, right? So if you look at it, the crash, this is it at the processor clock speed, which is gigahertz, right? And then we know that scan period is about 1 to 300 hertz, right? And then because of that, we believe that we only need 1 or 2 delay queue here, and then the recovery time it is very quick. It's within one. Generally, it's 1 epoch. It can be a little more, but generally is 1 epoch. And then there is the time that physical system can tolerate. That is the inertia. This varies significantly, but it's a large number of epoch in general. It's an order or 2 of an epoch. So here, what we see here is that, the quicker the system can crash, the smaller delay queue is, the shorter erroneous period that we have. Basically, the system is less disrupted that way. So this is kind of create a paradox that brittle is actually better, right? Which is nice. Next slide. So here is the way we kind of look at or see whether the system fall under the BFT++ criteria. So on the Cyper allowance, on the Cyper side, there is the Cyper allowance. It is basically the number Cyper cycle within an epoch and slack within an epoch, right? And then there is a physical tolerance, which is the inertia. Right, and then we take an example here, like let's say a medium class embedded processor at 1 gigahertz and a control loop of 100 hertz. This is actually the 747 inner loop. The outer loop of 737 control is actually 10 hertz. The inner loop is 100 hertz. So if you look at it, right, within a single epoch, we have 10 million cycles. And generally, and here we assume that we have 10% slack, which is 1 million cycle. But in general, the slack is more like 40% rather than 10%. So in general, what we expect that attack happen early in the input, because it's very hard to make an attack happen late. And we have a lot of time to crash and recover. Right, and the worst case attack happen at the last moment. But even if in that case we still have a million cycle to crash, which is going to happen. On average, properly diversified system crash within 5 to 10 cycle, 10 clock cycle. Right. So yes, we have we only need 1 or at most 2 slots for delay cycle, and also the recovery time basically calculate is about 1 epoch, a little more about 1 epoch. And can the physical system inertia tolerate that? I think so, right? So this is the proof where PFT++ can work. Next slide. So at ONR, when we did this, we have several different version implementation of it. I mean, I initially talked to people in the university. I talked to Georgia Tech, Wenki Lee and Tai Soo Kim. They have their own version, PFT++ version 2. This is where they actually distribute protection. So they protect each of their component and they protect it differently. This is good, it's more robust, but it's also a lot more expensive, right? And then I talked to Columbia University, this is Simha Situmadhavan and Yunfeng Yang. They have a different take. They actually, what they do is they create a nursery of pre-diversified component, and then they just keep, they are periodically resetting the system, whether or not there is an attack. And every time they restart, they use a different version, right? So this is lightweight. There is no redundancy required, but the protection is somewhat probabilistic, but it's still pretty good, right? And also, even if there is an attack, the attacker can only have access into the system or can only do something wrong within their period reset cycle. So there is that one version, which is lightweight. And the original version, I asked NRL to do it. Rather than putting it on the BFT system, which is 3 component, they put it on QRC. So this is basically QRC++. And this is this is as we described earlier, right? And then we later on come up with something else. Since the first version, we call it vanilla version. So the variation of that vanilla version, we call it RAM racing. In this case, what we did was, rather than diversifying using a diversification tool, we actually just diversify the processors. You have the primary and the backup are exactly the same. Let's say it's x86. We have a canary that is probably an ARM, right? So if there is any attack on so the difference between the primary and the backup is the backup has the delay queue, the primary does not, and we can ping pong them. So if there is an attack, the attack is for x86, it's gonna crash the ARM version, right? It's guaranteed. So that crash can trigger recovery. Basically, now you swap the backup and the primary during reset. So that's the next slide. So with that, we can implement, in any configuration of redundancy. Next slide. So what happened is the attack keep on coming, right? So inertia gives you a tolerance, a physical tolerance, but it also limited, right? How far can the inertia tolerate? So the nice thing here with the PFT++ is that the attack factor is actually captured in the FIFO. So we can actually use this and create a filter and preventing from ever coming back. Next slide. So the problem is we are doing it at the control level, and the PLC bus is actually a broadcast mechanism. There is no way for us to be able to filter. So what we introduce is we introduce a shim at the bus driver level and insert filtering capability there. So we basically turn a broadcast bus mechanism into a hub and spoke that we can do filtering. An additional benefit of this filter is actually we can do mode-based operation. Basically, we can define a certain mode of operation where and whitelist all of the potential, all of the valid comment in that, and we drop anything that is invalid, right? So this creates another protection. This will prevent stucknet from reprogramming the controller. And the only thing we need to protect is the change of the mode. That's something we need to protect. Next slide. So this is built at the UCSB, and there is a software version which is built at the UCSB and Boston University, and this basically takes resource from the controller itself. So depending how much, so this creates a limit of how much we can filter. And there is a hardware version. This is basically a card that we insert between the PLC bus and the controller itself, and this carries its own power, so it can do a lot more, but it's also more expensive to do. So next slide. So now, I mean, we built this. Some of the thing is actually implemented or being deployed in the Navy. I know that the YOLO, the Columbia version, is actually used, trying to be deployed as a protection on a missile launcher. The knowledge that we built using PFD++ is not very common. It's not well published. Not too many people knows it. So we MITRE is actually having a reference design for PFD++, and they prove that this can work, and they actually use they initially use work with Professor Tsoukalas on trying to model the protection, PFD++ protection on the SCRAM process. And later on, they implement it as in their lab, and able to kind of have that be stable under cyber attack. Next slide. So that's their setup. Next slide. And they basically use the normal PFD++ and prove it works. So for SCRAM. And next slide. So this is the future things that I'm gonna do. This is PFD++ require redundancy. Some of them don't require redundancy, but it's probabilistic. I want to have deterministic without redundancy. So this is the next version of it. Next slide. So there are many ways to do this. We can combine a lot of the technique that we developed earlier within here. Now I have to go into the sub process of the within the PLC program. Next slide. So PFD++ also is applicable for something beyond strict CPS. This is what we call virtual inertia. Like a radar. On the radar, the scanner itself, the radar has periodicity. The target does not move. Does not has an inertia. It cannot move very quickly, right? So with that, we can apply PFD++. And then there are other stateless systems like UDP or streaming that we can also apply that. Anything that can tolerate more disruption, that works. PFD++ works, right? I mean, next slide. So in summary, ONR invented this PFD++, and it leveraged physical property to actually build a cyber attack resilience system. And it is agnostic to the actual vulnerability and the actual attack. It does not require any probe or anything else. The only thing we need to detect is crash. And we also developed the shame mechanism to basically blacklist attack from recurring. And then it create another feature like a mode-based whitelisting of the operation. And there is many ways to implement PFD++. This is just a concept that's general enough, and every time we want to implement, we have to analyze the system and see which one is better. It's also somewhat, can work in a non-CPS system. I think that's all I have. Next slide.
I have a question.
Mm-hmm.
Yes, I have a question.
Yes.
I heard the term Byzantine fault for the first time here. I'm intrigued by the word Byzantine. Could you explain what a Byzantine fault is?
I think this is the Byzantine general model problem, right? So you ask 3 different people, and then you see how you look which one has, you try to detect the one that is cheating by basically looking at the stat, how many are the same and how many are not the same, right? So that's that. So that it is used in the cyber-physical and the fault tolerant, basically voting system. You always take the, because it's 3, there is always a majority. You take the majority.
Thank you.
I'll come back to my question.
Yes.
At Georgia Tech, do you play war games, cyber war games?
I don't, but there are other people.
Well, the reason I say that is in the Defense Department, they do this all the time.
Yes.
Because if you look at the penetrator armor analog to your cyber attack, it's a matter of if you build a better armor, you put your attention on building a better penetrator.
Yeah.
When you get a better penetrator, you go to a better armor. So we've gone from high density uranium penetrators to shaped charges. In the case of armor, we've gone to ceramic armor and the sheet armor and now active armor. And so, the attack doesn't necessarily have to be a single mode attack. It could be a repetitive attack, which would take up all of your time margin for recovery.
No, that is true, right? That's why we implemented the filtering mechanism. But in order to attack like that, in order for you to be able to keep on attacking, you have to compromise some other system. You already have to own some other system in cyber, right? Because otherwise you cannot do that. So my assumption, there are 2 assumptions here. One is that if all of the systems are protected this way, nobody can own a system because it always crashes before you can own it, right? So this is the nice thing. So I learned this in the old days from AIDS infection, right? So the reason why AIDS or HIV is very difficult to cure is because you cannot isolate the system. It dies before you can do that. Right, so this is why sometimes brittleness become a defense.
Yeah. Okay. Well, I see your point.
Thank you, Arden. Thank you, Colonel. And this is just so fascinating, and I like your analogy with with the Byzantine fault tolerance. I just wanted to say something for Nick Sulfanidis. The Byzantine great General Belisarius. In order to address this challenge, he relied very much on education. And I think maybe a Byzantine emperor later, after Justinian, wrote a manual, secret. They had a lot of secret reports. The whole problem was how do these generals get situation awareness when at that time they were, 500 miles apart, 1,000 miles apart. No telegraph, no internet, and there was a lot of space for deception, for, how did they reach agreement, right? How did they know what was happening? And, the practical answer they got on the field is education. They wrote a lot of manuals like Strategicon, where they had a lot of conventions, without knowing to be able to anticipate and guess right. And sometimes they guessed wrong, and we all know what happens then. Carnot, thank you. This was just smashing. It's very fascinating. I wanted to say that we had the chance under Carnot's guidance to try some of this in the Purdue reactor. So we have a modicum of confidence that when you digitize, you can protect your controllers from cyber attacks. And there's a lot more that needs to be done. The length of the queue can be AI, can be machine learning, determined dynamically. But my student, our student Stella Padopoulou, did her master's thesis on that and did a great job. And thank you very much again. Thank you, Professor Martoguno. So we moved to the next, with a little bit of delay, we moved to Dionysios Alibrandis. Dionysios is a professor here at Purdue. He is a power professor. He's a Purdue alum also. He's a great, friend and colleague, and he is an outstanding professor in teaching and research. He's gotten many awards, including the Outstanding Professor Award from the Eta Kappa Nu. The Eta Kappa Nu is the Honor Society of Electrical Engineers. Because we're running a little late, I'm not going to go through and read the litany of awards and, fine contributions that Professor Alibrandis has made. Dionysios, are you there?
Yes, I am. Can you guys hear me?
Right, so the floor is yours. Thank you very much for being with us this morning.
Thank you, Professor Tsoukalas, for the kind invitation. My name is Dionysios Alibrandis. I'm a professor of electrical and computer engineering at Purdue. And first, I would like to congratulate you on the successful launch of your center, CiENS. This center is very important and timely, as I hope it will stimulate research that is urgently needed for our energy infrastructure. So let me try sharing my slides here, and let me know if you cannot see them.
Yeah, we can see them now. Thank you.
Okay, great, great. So my presentation is titled Electrifying the World for a Sustainable Future. I walked in a little bit late because I was teaching a little bit earlier today, so hopefully I won't be too repetitive here. But in this presentation, I would like to share some of my views on sustainability and electrification, which is closely related to our electric grid. And I will conclude this by highlighting some of our ongoing research activities at Purdue. So I would like to think that all of us are here because our work entails in some way or another research, teaching, or other activities whose ultimate goal is to ensure that human civilization can thrive on planet Earth for many years to come. And as you all know, there is a constant friction between economic growth and the ability of our planet with its finite resources to sustain this. So the concept of sustainable development has been introduced to help us inform and shape our policies and aspirations. And there are many definitions of what sustainability means. Perhaps the most well-known is by the Brundtland Commission, which states that sustainable development is meeting the needs of the present generation without compromising the ability of future generations to meet their needs. So sustainability is indeed a grand challenge that modern society faces and has many different aspects. One key aspect that is very tightly related with our energy infrastructure is the issue of climate change. So one of the most authoritative reports on climate change is the one published by the IPCC, the Intergovernmental Panel on Climate Change. And of particular interest, at least to me, was a report on the physical science basis. This latest report was released in August of 2021, and it is almost 4,000 pages. And it contains a wealth of information. It talks about the current state of the climate, possible climate futures, risk assessment and regional adaptation, as well as ways to limit future climate change. And one of the strongest conclusions of the report is that there is now unequivocal evidence that indeed human influence has warmed the climate at a rate that is unprecedented in at least the last 2,000 years. And in this plot, I'm not going to describe in a lot of detail, but it basically shows the change in global temperature starting from the beginning of the industrial era around 1850, 1900s, and how it has evolved over the years, and how scientists now can do complicated simulations with confidence intervals and tell us that yes, indeed, it is human activity that has caused this change. So I would not read this report at bedtime. The key findings are sobering. Observed warming is driven by emissions from human activities. The scale of recent changes are unprecedented over thousands of years. Human-induced climate change is affecting many weather and climate extremes. Global surface temperature will continue to increase. And with every increment of global warming, changes get larger in mean temperature, precipitation, and soil moisture. And the extremes that we encounter are larger in frequency and intensity with every additional increment of global warming, which also has an impact on our power grids increasingly, more often. One observation that I found very interesting is that the global warming is very strongly correlated with CO2 emissions. And one thing that I learned by reading the report is that there is a near linear relationship between temperature increase and cumulative CO2 emissions. So the slope here is about 0.5 degree Celsius per 1,000 gigatons of CO2 emission. And of course, this is a graph of global surface temperature as a function of cumulative CO2 emissions since about 1850. So hence, we have a carbon budget. There's a carbon budget in terms of how much CO2 we can still emit if we would like to hit our temperature increase limits. And this plot shows various future scenarios. And so, for example, if we would like to limit the global surface temperature increase to 2 degrees, we have a remaining carbon budget of about 1,500 gigatons of CO2. And just as a point of reference, last year in 2021, the global energy-related CO2 emissions were around 35 gigatons. So that does not leave us a lot of time to act. The report suggests that the pathway for limiting future climate change requires limiting anthropogenic cumulative CO2 emissions, reaching at least net zero CO2, at least. And also we need strong and rapid sustained reductions in CH4, methane. The suggested mitigation pathways are characterized by energy demand reductions, decarbonization, and electrification of energy end use, as well as reductions in agricultural emissions and some form of CO2 sequestration. But I have highlighted the items in blue, decarbonization and electrification, because our work, and I believe the center's activities on advancing our energy systems can and should aim to directly impact these very important metrics. So electrification, in my opinion, is really the key for decarbonization. So I will proceed with a quick overview of the current state of our electric grid in the United States. So indeed, the grid is the largest and most complex machine ever made. And I will show you that in a minute. And so the key question is, where does our energy come from today? So in the continental US, we have three grids, actually, three main grids, which are called synchronous interconnections. And these are three huge, semi-independent, and extremely complex systems. We have the Eastern interconnection, the Western interconnection, and ERCOT in Texas. And this means basically that we can literally identify a network path from, for example, the outlet where my coffee maker is at home, through the medium and high voltage grid, to President Biden's, for example, TV in DC. Everything is connected. The whole system is one huge system. And the power grid is indeed a marvelous technological achievement that has served us extremely well over the past decades. Now, the grid used to be monolithic, but it's no longer monolithic. It's no longer a vertically integrated system. There are organizations called independent system operators, whose footprint covers most of the US today, that run daily markets of electricity. think of them as stock markets where generators and load serving entities submit offers and bids of energy. And the price of electricity is determined as the solution of a very complicated mathematical optimization problem, which tries to maximize social benefit, reducing the cost of electricity and so on, while satisfying power flow and reliability related constraints. So it's not just the cheapest solution, it's the cheapest subject to physical constraints and reliability constraints. And it's interesting to note that the price of electricity also varies by location, and it's called the locational marginal price. And this figure that I have here on the left tries to illustrate this concept. Now, this type of grid operation, which is relatively recent, is a major technological as well as policy-making achievement. This was not easy to achieve. And interesting enough, at the moment I took this snapshot in my computer, the prices were actually negative up there in Minnesota. And this is most probably due to congestion in the transmission system. And it means that if you're in Minnesota, you would be paid to consume more electricity if you were a load, or if you're a generator, you would be paid to reduce your production. So let's take a quick look at our primary energy sources. Where are we today? So this is called a Sunkey Diagram. This is the 2020 energy flow in the United States. It comes from Lawrence Livermore National Lab, which shows primary energy sources on the left and the consumption by the four major sectors of our economy on the right. And in 2020, in the US, we consumed a total of about 93 quadrillion BTUs of energy. And here's where you obtain our electricity from. So number one source of electricity today, natural gas. You can tell this by the width of these colored lines. Number two, tied approximately with nuclear, coal. Coal is the black line, nuclear is the red line. And then we have wind energy that has actually surpassed hydro, followed by solar, which is the top yellow line. And then we have a little bit of geothermal and fraction of energy from biomass and petroleum for electricity. Now, decarbonization, what we want to achieve implies reduction on our dependence on fossil fuels. So the key thing, if you look at this energy flow diagram, is to electrify the transportation sector. This is a key aspect of should be a key aspect of our decarbonization efforts, in tandem with increasing the penetration of renewables and nuclear power, non-carbon sources in the energy mix. Because if we keep burning coal and natural gas to create electricity that then goes to our vehicles, we're not really solving the problem. So this means that we want to increase the orange arrow flowing to the transportation sector, which means electricity, and put an X as much as we can to the petroleum use for transportation. And transportation is a key aspect because it's about a quarter of our total energy use in the United States. It's huge. So the automotive and aerospace even sectors have been embracing these new electric propulsion technologies very, very rapidly. As you probably know, many major automotive manufacturers have publicly revealed their plans to produce only electric vehicles within the next few years, 2025, 2030, 2035, literally tomorrow. And this is like a revolution that's happening in front of our eyes, perhaps more quickly than we realize. However, there still remain questions regarding the ability of our grid to support this humongous new additional load, as well as the supply chain of raw materials that would be needed for batteries and other components. In terms of our supply side, this is a historical review of the last 70 years or so of our electricity generation. You can see clearly that coal is no longer the king. Coal would be the black line that has been dropping over the last 15 years or so. And now the new king is natural gas. However, the green line, which is the renewable energy, has also been increasing very fast. Now that green line includes hydro, which is more or less constant, but hidden inside there is the exponential increase of solar, which rises very, very quickly and probably will surpass wind very, in the near future, as well as wind turbines. Just looking at the news, recent news, President Biden has pledged to cut our nation's fossil fuel emissions by 50% by 2030 by designing policies to promote the use of EVs and clean energy, such as wind and solar. And in particular, this administration has pledged to build 30,000 megawatts of offshore wind, which is about 2,000 turbines in the US by the year 2030. The Infrastructure Investment and Jobs Act, HR 3684, includes $73 billion for the electric grid. In Europe, there's proposals that if passed, we would see the last gasoline or diesel car sold in the EU by 2035. They would require that about 40% of all energy come from renewable sources by 2030, and they would increase the price charged for carbon emitted to make the use of fossil fuels increasingly expensive. However, the increased penetration of renewables is a huge challenge because these are intermittent, non-dispatchable resources. We don't really directly control them. And to maintain the stability of the grid, we need to maintain a continuous balancing act of supply and demand that needs to be satisfied all the time, every millisecond. Otherwise, we have a blackout, basically. So we are faced with a tremendous planning and operation problem for the grid. And in addition, our grid remains a prime target for malicious actors, cybersecurity. So there is an increased need for more intelligent approaches in designing and running our power system. And I'm confident that CiENS will play a key role in this aspect. So I would like to conclude this brief presentation by presenting some information how Purdue aspires to be a leader in this area, some other activities other than CiENS. Within my parochial, let's say, school of ECE, Electrical and Computer Engineering, we have the Schweitzer Power and Energy Systems area, which remains very vibrant, perhaps most vibrant than ever, and remains active in many aspects of power engineering. We currently have 5 core faculty in our area, and we have been collaborating with many esteemed colleagues from the School of ECE, Industrial Engineering, Mechanical Engineering, Civil Engineering, as well as others. And our research has been generously supported by various federal and state agencies, and as of lately, the automotive industry, which has been absorbing, as you can imagine, many of our recent master's and PhD graduates, like the Fords, the Teslas of the world. In our area, we focus on the technology of electrical power engineering. We really are the people that will study how all these resources are integrated with the power system and focus on the details of designing the power electronics, the novel machines that are needed, motors for electric vehicles, controllers, and so on and so forth. Now, I would like to conclude by highlighting an NSF engineering research center that we are very proud to be part of. It's called Aspire. This is the flagship program of NSF, the ERC program. And Aspire stands for Advancing Sustainability through Powered Infrastructure for Roadway Electrification. This center is led by Utah State University with major partners Purdue, University Colorado Boulder, and University Texas El Paso, and our international partner is University of Auckland in New Zealand. This NSF ERC is focused on EV technology and infrastructure. It's funded by $50 million over 10 years, and it's the only ERC focused on electric transportation. Besides our research and innovation activities, our center pays a lot of attention to engineering workforce development and diversity and culture of inclusion, which are key aspects. And the Purdue Aspire team involves faculty from civil engineering, electrical and computer engineering, engineering education, as well as political science, because we realize this is a very multidisciplinary problem. It's not just about, you know, designing new motors. What the center envisions is really a seamless, affordable, and ubiquitous charging across transportation modes and vehicle classes, as well as in urban and rural areas. And perhaps if you can focus a little bit on this graphic that I have on the bottom, one of the focuses of our research is wireless charging, either stationary or in motion, dynamic. So the activities of our center include all aspects of integration with the grid and renewable energy resources, as well as smart and secure charging management algorithms. So I believe this is an area where we could envision synergistic opportunities for collaboration with CiENS. So thanks for your attention. This concludes my brief presentation. Again, I really appreciate this opportunity and congratulations again.
Thank you, Yusuf. You really electrified our imagination. This is wonderful.
I've got a couple comments.
Please, Dr. Bement.
One way of doing transportation is through electromagnetic induction, especially for buses and for cargo movement. This is already at a pretty well advanced stage in South Korea through primarily the work at KISS, Korean Institute of Science and Technology. Mm-hmm. So that's one thing that I haven't heard very much about. The other thing is certainly we want to take advantage of wind energy along the coastline, but the models that have been developed by the University of Colorado at Boulder and tested out in not the large computer out in California, uses a tornado alley through central U.S. from Texas through Oklahoma all the way up to North Dakota as the primary place for placement of wind turbines. So, you know, why not use both? There's a tremendous amount of possibility.
Yeah, thanks for your comments. With regard to the work in CASE, Korean Advanced Institute of Science Technology, yes, we are aware of that work. And we are going past that. So CASE has demonstrated wireless charging for buses at low speeds and relatively low power levels. What we're trying to do here is demonstrate it at highway speeds and at power levels that have been unprecedented.
Yeah, that's quite different.
Yeah, it is quite different. And we are, you probably don't know this, but stationary wireless charging is well established. There are Society of Automotive Engineers standards in place. It's a technology, you know, there's a whole ecosystem. You can find products on the market. Dynamic in motion wireless charging, the standards are still in development. We are actually involved in those discussions right now. We're in those committees and we are trying to help, you know, inform with our analysis, you know, what the standards basically will describe. With regard to the second question about offshore wind, yes, of course, I was not advocating that we should only put it offshore. I was just saying that reading the news, offshore in this country, although it has been developed in other countries, apparently is getting a boost. We have a lot of offshore potential in this country, and the advantage of offshore is that it's next to our huge population centers. That's the biggest advantage. Whereas the tornado alley, let's say wind energy, is relatively away from where people live. And then you have other issues because you need to build up your transmission system.
Right.
But of course, we need to use all of our resources, not just a single one. I agree with that. Thank you.
Thank you. Thank you, Arden. Any more questions for Professor Elbrandis? Well, Dionysi, thank you so much again. We'll be in touch. Congratulations on the great work.
Thank you very
And
much.
we'll look forward to working with you and picking your brains, sharing your wisdom with us very generously. We're absolutely grateful for that. Thank you. So we move on to the last speaker, not least though, Dr. Federica D'Arema is a senior scientist, has a long bio, which I will not read in the interest of time. Dr. D'Arema is on the advisory board of CiENS. Federica, can you hear us?
Yes, I can. I'm trying to
Okay.
to switch to slideshow.
Her long and illustrious career did start with nuclear physics, an undergraduate from University of Athens in nuclear physics. She's been with Purdue activities for many years. I think this is the the latest and greatest past her service as director of the Air Force Office of Scientific Research, is consulting with the International Network Generations Roadmap on the IEEE on efforts to bring the 5G. A lot of the big data and the cyber physical security has to do with identifying and utilizing the dynamics of the data. The data is just too numerous to be able to look at it individually. And Federica has the definitive paradigm, the dynamic data-driven application systems. A lot of scholarly activity around the world is using the DAS. So without further ado, thank you again, and I will turn the floor to you, Federica.
Thank you, Lefteri. And can you see my screen?
Yes, we can see it.
Okay, thank you. Thank you, and greetings to all, and especially to Arden. Arden, very nice to see you. I'm glad to be part and contribute to the science efforts, and delighted to participate in this inaugural event, I should say up front. And science is an important mission for Purdue and for the broader society and industry sectors in the US and worldwide. So I view the science scope and green energy infrastructure, the title of my presentation, span the range from energy production to distribution, delivery, and use, consumption of energy services, as also Vivek, Lefteri, and others earlier mentioned. In my comments, I will discuss methods for optimized and adaptive design and management of such infrastructures, addressing end-to-end and systems of systems, the range of the energy aspects I just referenced. So in next slide, I would like to put into perspective what I'm going to discuss, and I'd like first to speak about the broader landscape. Systems of today and those foreseen in the future, be they natural, engineered, or societal, will provide unprecedented opportunities for new capabilities, but also present concomitant increased levels of complexity and heterogeneity, multi-level, multimodal, multi-scale, dynamic, and the ensuing systems of systems and also their complex systems need advanced methods of analysis and management, because no longer is sufficient to just understand a given phenomenon in isolation or design in isolation a component in a system. So we need methods not only to design, but also methods to manage and optimize the system's operational cycle, fault tolerance, evolution, interoperability with other systems, maintenance, and so on, and throughout the system's life cycle. And of course, energy infrastructures are a premier example of such systems. as are the energy infrastructure cross-links with communication systems, transportation infrastructure, weather prediction, and more. To support such complex and dynamic systems and systems of systems, no longer ad hoc methods are sufficient, and that goes also for the notion that data as the fourth paradigm. In my view, data is the primordial paradigm. We had data before we formulated theory, modeling, computational modeling. And moreover, in complex systems and systems of systems we deal with, increasingly we will deal with also, data analytics is not enough. We need systems analytics. And for that, ML alone is not enough either, I say. So we need more comprehensive systems models that are cognizant of the makeup, the characteristics of the system, and relevant aspects, for example, the physics of the systems. But such models traditionally have been used for the design cycle only, and not the operational cycle, because they are compute intensive. The dynamic-driven applications paradigm allows overcoming such impediments. And in the right-hand side, I have the schematic that depicts the DDS paradigm, which allows comprehensive models to represent and analyze a system or component, and in particular, real-time decision support for the system's operational cycle. So in DDAS, the executing model of a system can incorporate additional data, archival or corrected in real time, and this can make the model execute faster by replacing targeted parts of the computation with actual data. It can also make the model more accurate using the actual data for aspects of the system not well represented by the model. And in reverse, the model can control the instrumentation to seek or collect additional data, thus creating methods of cognizant coordination of multiple heterogeneous collections of sensors and controllers. And I want to also emphasize how these approaches can allow use of full-scale models sped up through DDAS, thus delivering capabilities for decision support with the accuracy of full-scale models as one of the major advances that have been demonstrated through DDAS, both for power grids, but also a host of other applications. And in the feedback loop control between model and instrumentation reminds me of Sukarno's diagram on cyber-physical systems. And so DDAS is a more comprehensive approach that preceded actually cyber-physical systems by several years. And but nevertheless, the CPS kind of aspects are a subordinate or a encompassing part of DDAS. And I can discuss this a little bit more later. Also want to point out here that DDS environments integrate the high-end computing with the real-time edge computing and IoT, and benefit from the increased computational speeds as well as the increased bandwidths and data transfer rates of the 5G and the future beyond 5G or B5G networks and communications infrastructures. And commensurately, and in a bootstrap way, the kinds of DDS-based infrastructures can also be applied for the operational management of the multi-level, multimodal, complex 5G and B5G infrastructures, and I'll discuss that later. And also I'll discuss a bit later related items, autonomy, AI, and ML. And also I want to point out that DDS changes the test and evaluation notions in very important ways, for example, making T&E part of the life cycle of systems. And in subsequent slide, I'm also going to discuss how DDS is used in power grids as well as other application areas related to energy production, distribution, delivery of services, cognizant of time-dependent and changing demands, environmental factors, and a host of other factors relevant in the scope of intelligent energy systems. So the onedds.org website is a repository of DDS-based work conducted by the research communities, including many Purdue faculty and students, and I'm very grateful for their contributions in this initiative, so the DDS initiative. So in the next slide, I'd like to provide some examples of DDS-based modeling of complex systems and how such advances can be put back to back to provide optimized operations capabilities for systems of systems. So starting from the example in petroleum exploration, which has been the area that inspired me to think of DDS and the DDS paradigm in the early 80s, when I was at Schlumberger Dollar Research and did work on Monte Carlo and discrete ordinance modeling with instrumentation that involved linear accelerators and neutron and gamma ray scattering measurements that were used in the models to infer porosity and rock formations composition and identify the petroliferous areas. At that time, I thought of the three tenets, the key ideas of the DDS: replace parts of the computation with targeted data to speed up the model, improve the accuracy of the model, and model control of the instrumentation. But in addition to my concerns and thoughts of how do you prove convergence of computational models, Monte Carlo, including Monte Carlo, include statistical, but more discrete ordinance PD solvers under perturbations of the stream data. But also at that time, DDS was also premature because we only did batch computing. And it was later with the advent of other work I did, including the advent of high performance parallel and distributed computing and asynchronous algorithm work that I did in the mid 80s, where I thought the paradigm could be pursued and spoke about it calling the idea the Gedanken laboratory then. And then over time, with confluence of other important additional advances, such as ubiquitous sensing and increasing computer and networks speeds. In the late 90s, I launched the idea through the program activities at NSF, and I started funding work under the DDS rubric. So in addition to work that I supported in oil exploration, such as the work that is depicted in the graphic by Mary Wheeler, I also supported several projects on electrical power grids, including work by Professor Tsoukalas. And the graphic here is work of a multidisciplinary collaboration on multi-level, multimodal, multi-component structure of power grids, Dds-based for detection of onset of surges and other disruptions of traditional energy sources, to provide real-time decision support with the accuracy of full-scale models, for example, mitigation impact and so on. And also I supported work on Dds-based optimization operation of continuous health monitoring of wind turbines. And this is an example of continuous T&E that I mentioned earlier on for optimized operations of individual turbines here, as well as optimized adaptive management of distributed collections in wind farms, of turbines in wind farms. So looking at power generation distribution and delivery, not only from the perspective of energy sources and energy grid health, but also how its operation can be impacted by adverse weather, tornadic activity on the top left-hand side, and hurricanes in Katrina-like scenario on the top right-hand side, in order to factor such decisions for power grids and energy demands and delivery. And also these two applications, areas themselves, hurricanes and tornadic events modeling, also benefit from DDS-based methods to improve, for example, prediction of such events. And then this can be combined so that one can, in a sense, understand how they could impact power grid operations, as also Librandis mentioned earlier on about the events in Texas last year, for example, the snowstorms and other catastrophic events over the last year. Provide support for other smart city energy needs and consumption.
Frederica, we lost your voice. Hello?
Yes, 1 second. Yes, I got muted by mistake, sorry. So providing end-to-end support for other energy needs and consumption, one can leverage and integrate inputs from work in other areas also. For example, transportation infrastructures, and then together with communications, cell phone activity track, for example, and optimize efficiencies in transportation infrastructure, which is also, as was mentioned earlier on, it goes in tandem with our kind of production of energy to, in a sense, efficient use of energy. And also now with the advent of electric vehicles and prevalence and expected predominance, the efforts of how to support the concomitant energy variable critical needs for power grids is also important. And here's an example that I will discuss more in the next slide. In this example, a real-time assessment and operational management for complex power grids is shown in the context of Dds-based methods. Today, power grids comprise of a range of energy sources. It was mentioned also earlier on previous speakers, traditional carbon-based power plants and the like, which provide constant and predictable energy production, and also renewable energy sources, solar, wind, which are variable. And all of these together with microgrids comprise the emerging power grids infrastructure of today. And so this power grid is subject to variations and disruptions with renewables, which present conditions of variable energy production, as well as for traditional energy generation due to, for example, to overloading failures of transformers, adverse weather-induced disruptions, and other. And in general, there is variability in energy production, in transmission, and in consumption, as there are also variable types of consumers and time-varying levels of energy demands, priorities, for example, hospitals, factories, and other critical infrastructures. So the power grid infrastructures entail modeling of multiple modalities and instrumentation such as PMUs for tracking potential for surges and related disruptions, measurements of electric production, loss, continuous measurements of consumption, and with measurement models ranging from statistical to discrete event, K-means, fuzzy logic methods, and more. And the example shown here consists of 3 microgrids supporting 3 entities, each one with 3 levels of priorities: critical, non-critical, and regular. And the table shows how in the case of a disruption, in one scenario where the grids are isolated and the other where the grids can share resources, in both cases, the Dds-based decision support adjusts the power distribution accordingly to prioritize needs. And so the impact of the reduction of the energy available is mitigated considerably, or in some cases eliminated. And the DDS framework based here in representing operational aspects for energy service is also optimized in terms of energy efficiencies, emissions, cost reductions, or energy generation cost, energy distribution and consumption, as also factors that are important, as also Librandis mentioned in his presentation. And other DDS-based efforts have supported power grid security. And Arden asked the Sukarno how they, in a sense, can address the robustly the security aspects. And so we have funded research work, including work by Professor Tsoukalas on more robust methods. Methods also akin to those for power grid frameworks have been used for diverse applications in other areas. For example, in reactor system design, including the work of Professor Tsoukalas, in manufacturing operations, border patrol, and many others, to cite a number of examples here only now. And so all these applications, of course, use different kinds of instrumentation and not completely identical modeling methods as with power grids, but by and large share the commonality that they manifest multiple levels of heterogeneity in components and services, whether it's monitoring voltage in electric grids, or reactor operation, or tracking parts in a supply chain, or tracking and surveillance in border patrol. And all these applications have commensurate levels of modeling complexity and require computations that span high-end to real-time, large amount, and timely data transmission. So real-time control requires high bandwidth and low latency communications to avoid data rates and erroneous packet transmissions, which are detrimental, for example, on power grid operation and, of course, other application areas. And so the advent of 5G and the future beyond 5G networking advances are timely in that they can provide such needed services, such as enhanced mobile broadband, ultra-reliable and low-latency communications, massive machine-type communications, and massive IoT support, all capabilities that are needed for real-time control and decision support services in power grids. And in a bootstrapping way, the methods discussed here can also be used to support the power grid infrastructures and the like, and to support, for example, the 5G and beyond 5G infrastructures, as is shown on the bottom of the slide. And actually, there is interest from the DDS community to apply the approaches that and methods, the DDS-based methods that were developed for power grids, for example, in the case of communications and networks for 5G and beyond 5G to optimize operation, energy efficiency, security, and more for the design as well as the operation of the 5G and beyond 5G for CiENS. So in the next slide, I'd like to discuss about AI, ML, automation, autonomy, and DDAS. So automation has been at play for a while and has been pervasive in industry, manufacturing, aerospace, and other sectors. And its first major and spectacular success was that it enabled way back in 1969 for us to land on the moon. But over the years, many technological advances, including distributed, pervasive, ubiquitous computing, networks and communications, and the need to manage such resources gave rise to notion that is autonomic, for example, computing, and that notion then spilled over as autonomic operations, so more general for other systems. And in fact, today we talk about shared autonomy as human-machine collaboration as modalities of pursuing autonomy. And on the other hand, the concept of AI that is intelligent, that is intelligence demonstrated by machines with human-like abilities to learn, reason, plan, perceive, and process natural language. These go way back to more than 50 years now, when the methods and such capabilities, computing, for example, were not adequate. And at that time, AI overpromised and under-delivered, as the saying goes. And fast forwarding now, autonomy, autonomic systems, and the term AI has been resurrected. But even today, when we speak about AI, it is clear that AI capabilities we are developing are quite far from what the human brain can accomplish, such as cognition, inference, abstraction, problem solving, original out-of-the-box thinking. And on the other hand, today's computers can do computations with numbers at phenomenal speed that no human can match, no human brain can match. And these complementary capabilities of the human brain and the computer brain are important to keep in mind as we, in a sense, strive for AI. In addition, right now, consider 3 levels of AI: narrow AI, general AI, and super AI. But in fact, today, when we speak about AI, we really mean narrow AI. So we are far from, the ultimate. And also related to that, AI many times is conflated with ML. And also, as often, AI is conflated with data analytics. So ML and data analytics are successful in that respect in many applications, many of those that actually entail longitudinal analysis and allow training of the ML parameters and then apply similar classes of data. However, when we deal with systems with complex and dynamic behaviors and systems that are operating with other systems, introducing more complexity and dynamicity, ML alone is not capable to adequately represent such complex and dynamic conditions. And certainly power grids are a good example with many and multiple variable energy resources, consumers, varying levels of priorities, modalities, resources subject to other dynamic conditions, environment, destructive events, adverse weather, or grid component failures. And another area is in aerospace, aircraft safety under adverse conditions, turbulence and structural health monitoring and integrity or sensor failure. Such dynamic conditions cannot be analyzed simply by ML. So such situations create faults, pitfalls, because as the ML model evolves, there are the issue of transparency that is not fully understood how the ML model changes itself based on the training data, interpretability. It may not be fully understood how well the change algorithm still represents the system accurately or adequately, and whether the inferences for decision-making are, for example, still valid. So another aspect is whether the self-modified ML model uses appropriate data, or whether the skewed data create inadequate and inaccurate models or algorithms. So putting this together, the ML model can go rogue, as I like to call it, and such situations, who also is responsible for adverse effects of a rogue ML algorithm. The DDS paradigm, in distinction, avoids, although it is a learning model also, it learns from the dynamic data inputs. In DDAS, the model represents the systems cognizant of the characteristics of the system, for example, the physics of the system. And so the model in DDAS has these physics constraints to safeguard it from going rogue. And in ML, the physics is not explicitly represented. And so these are key and big differences between DDS methods and ML alone methods. On one hand, to avoid the ML model algorithm going rogue, perhaps an approach would be to continually validate the evolving ML model vis-a-vis its prior analysis. This is not new in nuclear industry. Nuclear codes upgrades were always validated in terms of their backwards compatibility. And that has been key operational process for adoption of the upgraded new codes in nuclear and also in aerospace sectors, for example. However, of course, this is computationally intensive. So it may be that another way for ML methods to devise safety bounds. For example, another test and evaluation, so in that case, test and evaluation becomes part of the life cycle of an ML-based model as the algorithm evolves. So maybe that is an application of this evolving test and evaluation and lifelong test and evaluation adaptation. So on the other hand, another fruitful way to use ML as part of the tool of the DDAS approaches. For example, select among the DDS model space. And in fact, such work has been done by a number of, pursued by a number of PIs in their own application areas, including the work of Wilcox in the area of aerospace applications. And my last slide, I would like to show a bird's eye view of the impact of DDAS. On the left hand, I won't discuss all here in detail. On the left-hand side, and the butterfly graphic spans a large number of areas of impact of DDS, from the fundamentals in physics to structural health monitoring, smart infrastructures, and more, and overall real-time decision support with the accuracy of full-scale models, capabilities that are needed in our quest for autonomic systems capabilities. And on the right-hand side shows how DDS has driven both the development of foundational methods as well as applications methods. For example, enhanced digital twin notion, where rather than the traditional notion where the model and the physical system are side by side in a static way, in DDS, we move to a paradigm where the model dynamically interacts with the physical system through the instrumentation. And of course, that changes the notion of the digital twin. And again, Wilcox's work on aerospace has adopted that as a DDS-based digital twin. or a dynamic digital twin. And likewise, the DDS paradigm has changed also the notion of data simulation in similar ways, and has also impacted important neural networks methods. And again, I mentioned CPS. Regarding CPS DDS, I distinguished from DDS from CPS in that DDS is a well-defined concept from the outset, assumes comprehensive models of the natural and engineered systems, and has defined how they interact with the instrumentation. Sukarno mentioned earlier on, CPS has some kind of a loose definition. And on the other hand, and hearing also Sukarno's presentation, I believe CPS can benefit from more comprehensive approaches of the DDS paradigm as a subset in some ways within the DDS paradigm. And the examples in the middle, in the butterfly, are depict a wide scope of the impact of DDAS. The graphics from a report, and also this and work done over the years and to the present can be found on the OneDDS website, and in a series of Springer book series of 3 volumes. The first one is in its 2nd edition, and both volumes 2 and 3 are imminent to appear in 2022. And with that, I want to thank you for the opportunity to share these thoughts with you, and I'm looking forward to work with you in the success and impact of CiENS. Thank you.
Thank you, Dr. Dorema. Thank you very much for the intriguing presentation. We have a question. Was there a question? Okay, I know it's kind of getting late before lunch, and we're standing between you and the, so we still have a little bit of time if you want for any general comments or questions. I
have one suggestion.
Go ahead, Arden.
The new center, the Center for Intelligent Energy Systems, has a possible connection with a new policy institute, which you probably know about, that Keith Kroc is establishing, which is sort of a bipolar institute connecting technology with policy. And a lot of what we've covered during this meeting fits in very nicely with some of the paradigms that they're going to be working with in order to do policy development. And in the energy field, this would be a very ripe area to establish a collaboration.
Right. Thank you. Thank you.
I have a comment. Very early in the meeting, it was mentioned not to concentrate on electrons only, but also look at the heat generated.
Right.
I hope the new nuclear energy systems look at that, because today's nuclear power plants have efficiency of about 33%, which means 67% of the energy is not utilized. So I hope the new system look at both the use of the heat and improved thermal efficiency.
Right. Thank you. There's a lot of things that can be done at the systems level, and especially also with hydrogen. Hello.
Terry.
Go ahead.
Can you? I'm not sure if you can see me. Can you hear me?
Thank you. Yes.
Okay, this is Panayota. I just wanted to make a very brief comment about engaging with utilities. I think they have really great data if they open their minds to share them. It'd be a good idea to try to engage some utilities in the region or across the country in the center. Mostly they have very useful data also on the demand side, because unless you are trying to innovate on the production side. But that's my advice.
Thank you very much. Thank you. And MISO is a possibility, Midwest Independent System Operator, who is nearby. We've worked with them in the past. So that's another great source of data on the demand, on the consumption, the demand side. Any other questions, comments?
I think you're off to a great start. This was a great first meeting.
Thank you. Let's get started. We'll have a symposium. The symposium.
Very interesting agenda.
We'll set the symposium. Hopefully, it will be a full meeting, and we'll send out timely notes. We'll have calls for papers and posters. Hopefully, we'll be on either March. It's not finalized yet. It's March 26th or May 3rd. We'll send out info to find a better day. Hopefully, we can do this here on campus. Well, we'll have a mixed thing, people from away via Zoom, and also people who could, congregate here and have a in-person meeting. So I know it's kind of getting late in the morning, and we're standing between the people here in West Lafayette and lunchtime. I cannot thank you enough. I cannot thank the executive board, Dr. Chen from the deans, Dr. Kim, the head of chemical engineering, Dr. Kim, the head of nuclear, Dr. Perulis, the head of ECE, Dr. Carava from civil, Dr. Dongyan Shu. Especially, I'd like to thank and recognize our advisory board, Dr. Biment and Dr. Spofford, Dr. Darema, Dr. Librandis, Dr. Gross, Professor Yong Chen from physics, Professor Saber Kais from chemistry, our dear friend, Professor Sander Goodhart from English department, LAS, Liberal Arts, Professor Sutherland from Tripoli, Professor Tsoufanides, Professor Sukarno Mertoguno. We have also an industry board, and we have Dr. Vivek Agarwal is there, and Dr. Padazopoulos, and Dr. Hivets, Mr. Tim Henley from Exelon. There are other people, Dr. Patel from Sandia. There are other people who need to clear their nominations with their, or get approval from their organizations. Hopefully we will hear from the executive board and the advisory board to have more people added, especially from industry. And Dr. Carava's suggestion to engage more the utilities as a source of data and know-how, and engage a lot of it, as Professor Libradis pointed out, has to do with the electrification of transportation. It's the biggest source of CO2, and of course also industry is a big source. So this scheduling, as a way of leveraging the best of energy resources, it's now possible with AI and ML and the DDAS issues and gifts that Dr. Darema went over, and all the reassuring and comforting notes about cybersecurity and Byzantine fault tolerance that Professor Mertoguno shared with us. Hopefully we will have a full-scale symposium, the first CiENS Intelligent Energy Symposium at the end of the spring semester. We would like to be in touch with you. Feel free to contact me anytime, and any ideas. We will have a full brainstorming in the end of the spring semester. Would like to pick your brains, to have your suggestions and strategies, and then get this approved by our board, our executive board, and most importantly, help us contribute to the development of new knowledge and the resources from the federal budgets, from industry, from benefactors, to be able to prepare the next generation of engineering talent, and the resources to make Purdue Science Center a material contributor to the green transition to net zero by 2050. This is it for me.
Great.
Again.
You haven't changed a bit.
You too, dear friend.
Little grayer.
Thank you so much. Thank you, everybody. Professor Kim, you have a word to say, or no? I see you. No, you are on mute. Well,
I just wanted to thank you, and thank you for the great start, and congratulations. Thank you.
thank you very much. So everybody, I think you are the one who deserves real gratitude to get this thing going, get it off the ground. Thank you so much. Thank you, everybody. Stay healthy, in good spirits, and we'll be in touch.
Great.